Welcome to this problem walkthrough. Today, we'll explore an intriguing problem titled Distribute Coins in Binary Tree. We'll break down the problem, discuss different approaches, and analyze their efficiencies. Let's dive in. The problem asks us to distribute coins in a binary tree such that every node ends up with exactly one coin. You are given a binary tree with n nodes, and the total number of coins across the tree is also exactly n. Each node in the tree has a value that indicates how many coins are currently at that node. To redistribute these coins, you are allowed to make a move where you transfer a coin from one node to one of its direct neighbors, which could be either a parent or a child. The goal is to determine the minimum number of moves required to achieve the desired distribution where every node has exactly one coin. The input is provided as the root of the binary tree, where each node contains its current coin count and pointers to its left and right children. The output is an integer representing the minimum number of moves needed. This setup ensures that we focus on the efficiency of redistributing coins across the tree. Let's look at the first example to understand how this works. The tree has 3 coins in total, all concentrated at the root node, while its 2 children have none. To balance the distribution, we need 2 moves. In the first move, we transfer one coin from the root to the left child, and in the second move, another coin from the root to the right child. Now, each node has exactly one coin, and the total number of moves required is 2. In the second example, the left child starts with 3 coins, while the root and the right child have none. Here, the first 2 moves involve transferring one coin at a time from the left child to the root. The third move transfers a coin from the root to the right child. After these 3 moves, all nodes have exactly one coin, making the total number of moves required 3. In the third example, the root has 1 coin, the left child has none, and the right child has 2 coins. The redistribution process begins by transferring one coin from the right child to the root. This brings the root's coin count to 2. In the second move, a coin is transferred from the root to the left child. At this point, all nodes have exactly one coin, making the total number of moves required 2. These examples illustrate different scenarios where coins are either concentrated in one node, or distributed unevenly across the tree, and show how the minimum number of moves is calculated to balance the tree. Now, let's discuss the constraints and edge cases for this problem. The tree can have up to 10,000 nodes, and the value at each node, which represents its coin count, can also go up to 10,000. Importantly, the sum of all the coin values across the tree is guaranteed to equal the total number of nodes, ensuring that redistribution is always possible. Some key edge cases to consider include a tree with only a single node, where no moves are needed, or cases where all coins are concentrated in one node while the others are empty. The solution must also handle trees of varying structures, from balanced to highly unbalanced, and efficiently manage both excess coins at some nodes and deficits at others. These constraints ensure that the problem is both challenging and solvable within the given limits. To start, let's explore the brute force approach as a potential solution. The basic idea here is to simulate every possible way to move coins between nodes in the binary tree. For each node, we calculate how many coins need to be added or removed to make that node balanced, and then repeat this simulation recursively for all subtrees. A key observation is that a node is considered balanced when it has exactly one coin. To achieve this, coins might need to be moved from its parent, its children, or even other distant nodes in the tree. However, this approach quickly becomes impractical. The reason is that simulating all possible moves leads to an exponential time complexity, especially as the size of the tree grows. For example, if the tree has more than 10 nodes, this method becomes computationally expensive and infeasible. So, while the brute force method gives us some intuition about the problem, its inefficiency makes it unsuitable for larger trees. Now, let's shift our focus to the optimized depth-first search, or DFS, approach, which is much more efficient. The central idea here is to calculate the number of moves locally at each node, based on its surplus or deficit of coins. Using a post-order DFS traversal, we can determine the net flow of coins needed from or to the node subtree and use this information to calculate the total moves for the entire tree. The key insight is that every node needs exactly one coin. If a node has more or fewer coins than this, the surplus or deficit can be calculated as coins 1. During the traversal, we process the children of a node first, calculate their surplus or deficit, and propagate that information up to the parent node. This ensures that the total moves required to balance the tree are accumulated efficiently. The algorithm involves a simple step-by-step process: perform a post-order DFS, calculate the surplus or deficit at each node, add the absolute values of the surpluses or deficits from the left and right subtrees, and propagate the remaining surplus or deficit to the parent. Because every node is visited exactly once, the time complexity is linear, O(n), where n is the number of nodes. The space complexity is proportional to the height of the tree, O(h), due to the recursion stack. This makes the DFS approach both time-efficient and memory-efficient. The optimized DFS approach emerges as the clear choice for solving this problem, and here's why. First, it processes each node exactly once, making it highly efficient for large trees. Its recursive nature aligns perfectly with the hierarchical structure of binary trees, making the implementation intuitive and concise. This efficiency and ease of implementation allow the algorithm to scale seamlessly with the size of the tree. Comparing this to the brute force method highlights the stark difference in practicality. While brute force suffers from exponential time complexity, DFS achieves linear time complexity, making it far more suitable for larger inputs. As for iterative alternatives, while they could eliminate the recursion stack overhead, they would introduce additional complexity in managing the traversal explicitly. This detracts from the simplicity and natural alignment that the recursive DFS provides. In conclusion, the DFS approach strikes the perfect balance between efficiency and simplicity. By leveraging the tree structure and solving the problem in linear time, it stands out as the most practical solution for distributing coins in a binary tree, even for very large datasets. In this problem, we are given a binary tree where each node contains a certain number of coins. Our task is to redistribute these coins so that every node ends up with exactly one coin, and we need to do this using the minimum number of moves. A move is defined as transferring one coin between a parent and child node, either upwards or downwards. To solve this problem efficiently, we use a post-order traversal of the binary tree. The main idea is to calculate the excess coins at each node, which is the difference between the coins it has and the one coin it should have. If a node has a positive excess, it means the node has extra coins to give away, whereas a negative excess means the node needs coins. Our goal is to ensure that the excess at every node becomes zero by redistributing coins across the tree. To achieve this, the first step is to define the problem in terms of excess. At each node, we calculate the excess as the number of coins at the node -1. Then, we use post-order traversal to process the nodes in a bottom-up manner, starting with their children before addressing the parent. This allows us to calculate the excess locally at each subtree and propagate it upwards to solve the global redistribution problem. Post-order traversal is central to our algorithm because it allows us to address the child nodes before considering the parent. The traversal proceeds by first visiting the left subtree, then the right subtree, and finally processing the current node. At each node, we calculate the excess of both the left and right subtrees. These excess values represent how many coins are needed or can be given by the children. The total number of moves required at the current node is the sum of the absolute values of these excesses, as each unit of excess represents a coin transfer. Once we calculate the moves, we compute the excess at the current node. This is done by adding the coins at the current node, subtracting 1, since it should retain one coin, and then adding the excesses from the left and right subtrees. This current excess is then passed upwards to the parent node, enabling the redistribution process to continue seamlessly. For the base case of our recursion, if a node is null, meaning it is a leaf node, we return an excess of 0 because there are no coins to redistribute. The key insight behind this approach is that by breaking the redistribution problem into smaller, localized problems at each subtree, we simplify the process of balancing the entire tree. Since we use post-order traversal, we ensure that all the child nodes are processed fully before addressing the parent. This way, the excess coins can be propagated upwards efficiently. Another important observation is that the number of moves required to balance a node is directly proportional to the absolute value of the excess coins being passed between the node and its children. This is why we use the absolute values of the excesses to calculate the total moves. In terms of implementation, we rely on the tree structure provided in the problem, where each node has a value indicating the number of coins and pointers to its left and right children. A recursive helper function is used to perform the post-order traversal, returning the excess at each node while updating the global count of moves. From a complexity perspective, the time complexity is O(n), since we visit each node exactly once during the traversal. The space complexity is O(h), which accounts for the recursive stack space, where h is the height of the tree. To illustrate how the algorithm works, let's consider a simple example. Imagine a binary tree where the root node has 3 coins, and both its left and right children have 0 coins. Starting with the left child, we calculate its excess as 0 minus 1, which equals minus 1. This means the left child needs 1 coin, so we return minus 1 to the root. Next, we process the right child. Similarly, its excess is also minus 1, so we return minus 1 to the root. Now, at the root, we calculate its excess. It has 3 coins, so its own excess is 3 minus 1, which equals 2. Adding the excesses from its left and right children, we get 2 plus, minus 1, plus, minus 1, resulting in an excess of 0. The moves required at the root are the sum of the absolute values of the left and right excesses, which is, minus 1, plus, minus 1, giving us 2 moves. Hence, the total moves required to balance the tree are 2. This example demonstrates how the algorithm propagates excess values upwards and calculates the moves required at each step. To optimize the algorithm further, we can take advantage of a few strategies. First, we avoid redundant calculations by storing excess values during traversal. This ensures that we don't recompute the same values multiple times. Additionally, excess values are directly propagated to the parent node without any intermediate steps, which simplifies the redistribution process and reduces overhead. These optimizations help maintain the efficiency of the algorithm, ensuring that we achieve the minimum number of moves with minimal computational effort. Here, we start by defining the treeNode class, which represents the structure of a binary tree node. Each node has a value, as well as optional left and right child nodes, which default to none. Next, in the solution class, we define the main function distributeCoins. This function is designed to calculate the minimum number of moves required to distribute coins across the binary tree so that every node has exactly 1 coin. To achieve this, we initialize a variable self.moves to track the total number of moves. Then, we define a helper function DFS, which uses a depth-first search approach to traverse the tree. The traversal is performed in post-order, meaning we process the left and right subtrees before handling the current node. The DFS function first checks if the current node is none. If so, it returns 0, as there's no excess or deficit of coins in a non-existent node. Moving forward, we calculate the excess coins from the left and right subtrees by recursively calling DFS on node.left and node.right. These values represent the surplus or deficit of coins that the left and right subtrees contribute to the current node. Now that we have the excess values from the left and right subtrees, we calculate the excess coins at the current node by taking the node's value, adding the left and right excess values, and subtracting 1. This subtraction accounts for the fact that each node requires exactly 1 coin for itself. The total moves required to balance the coins are then updated by adding the absolute values of the left and right excesses, as these represent the number of coins that need to be moved in or out of the subtrees. Finally, the function returns the excess coins at the current node, which will be used by its parent node in the recursion. After the DFS function completes its traversal of the entire tree, we return self.moves, which contains the total number of moves needed to achieve the desired distribution of coins. This completes the implementation of the solution. Here we start by defining the structure of our binary tree with the treeNode class. Each node in the tree has a value representing the number of coins at that node, along with references to its left and right child nodes. We also define 2 constructors, one for creating a node with just a value, and another for initializing a node with its value and its left and right children. Next, we move to the solution class, where we introduce a private variable, moves, to keep track of the total number of moves required. The main method, distributeCoins, begins by initializing moves to 0 and then calls a helper function, DFS, starting with the root of the tree. The DFS function is our recursive depth-first search method that processes the nodes of the tree to determine coin distribution. Within DFS, we immediately handle the base case. If the current node is null, we simply return 0, as a null node contributes no excess coins to the system. Now within the DFS method, we proceed with a post-ordered traversal, which means we process the left and right subtrees before handling the current node. First, we recursively call DFS on the left child and store the result in left excess, then repeat the process for the right child, storing the result in right excess. At this point, we calculate the excess coins at the current node using the formula, the node's value plus the left and right excesses, minus 1. The subtraction of 1 accounts for the fact that each node needs to retain exactly 1 coin for itself. To update the total number of moves, we add the absolute values of left excess and right excess to the moves counter. This ensures we're accounting for the coins moved both to and from the left and right subtrees. Finally, we return the calculated excess to the parent node, allowing the recursion to propagate this information up the tree. In this example, we have a simple binary tree where the root node has 3 coins, and both of its children have 0 coins. The goal is to distribute these coins such that every node ends up with exactly 1 coin. To achieve this, we use a post-order traversal, starting from the root and then processing the left and right subtrees. First, we move to the left child, which has a value of 0. Since this node has no children, the excess at this node is calculated as the total coins it holds, plus the excess from its left and right subtrees, minus the 1 coin it needs. This gives us an excess of minus 1, meaning this node needs 1 coin. We return minus 1 to its parent. Similarly, for the right child, which also has a value of 0, the excess is calculated to be minus 1, as it also needs 1 coin. Returning to the root, we now calculate the total excess at this node. The root has 3 coins, and it receives minus 1 from each of its children, so the total excess becomes 0. To balance the coins, we count the absolute values of the excesses from the left and right children, which together sum to 2. This means 2 moves are required to distribute the coin such that every node has exactly 1 coin. The output for this example is 2 moves. Now, we examine a slightly larger binary tree. Here, the root has 0 coins, and its left child has 3 coins, while its right child has 0 coins. Additionally, the left child itself has 2 children, each with 0 coins. Starting at the root, we first traverse to the left child, which has a value of 3. From there, we process its left child, which has a value of 0. Since this node has no children, the excess is minus 1, indicating that it needs 1 coin. We return minus 1 to its parent. The same calculation is performed for the left child's right child, which also has a value of 0. Its excess is minus 1, so we return minus 1 to its parent as well. Returning to the left child with a value of 3, we now calculate its total excess. It has 3 coins and receives minus 1 from each of its children, resulting in an excess of 0. The number of moves required here is the sum of the absolute values of minus 1 and minus 1, which equals 2. This value is returned to the root. Next, we process the root's right child, which has a value of 0. Its excess is also minus 1, as it needs 1 coin. Returning to the root, we calculate its total excess. The root has 0 coins, receives 0 from the left child, and minus 1 from the right child, resulting in a total excess of minus 2. To balance the tree, we calculate the moves required at this level as the sum of the absolute values of 0 and minus 1, which equals 1. Adding this to the 2 moves required earlier, we get a total of 3 moves for the entire tree. The output for this example is 3 moves. In this final example, we have a balanced binary tree. The root has 1 coin, its left child has 0 coins, and its right child has 0 coins. Additionally, the right child has a left child with 3 coins. Starting at the root, we first process the left child, which has no children. Its excess is minus 1, as it needs 1 coin. We return minus 1 to the parent. Next, we move to the right child, which has a value of 0. Here, we first process its left child, which has a value of 3. Since this node has no children, the excess is calculated as 2, meaning it needs to give away 2 coins. This value is returned to its parent. Back at the right child, we calculate its total excess. It has 0 coins and received 2 from its left child, resulting in an excess of 1. This value is returned to the root. Finally, at the root, we calculate its total excess. The root has 1 coin, receives minus 1 from the left child, and 1 from the right child, resulting in a total excess of 0. To determine the number of moves required, we sum the absolute values of the excesses at each level, 1 move for the left child and 2 moves for the right subtree, totaling 3 moves. The output for this example is 3 moves. The time complexity of this solution is O(n), where n is the number of nodes in the binary tree. This efficiency comes from the use of a depth-first search, or DFS, traversal. During the traversal, each node in the tree is visited exactly once. For each node, the algorithm calculates the excess coins in the left and right subtrees and then determines the excess coins for the current node. These calculations are constant time operations for each node. Since the time spent on each node is proportional to the number of nodes, the total time complexity becomes O(n). Additionally, the post-order traversal ensures that each subtree is fully processed before moving up to the parent node. This eliminates any redundant or overlapping computations, maintaining the efficiency of the algorithm. Therefore, the overall time complexity remains linear, or O(n). Now, let's talk about space complexity. The space complexity of this solution is O(h), where h is the height of the binary tree. This is primarily determined by the recursive call stack used in the DFS traversal. The maximum depth of the recursion stack corresponds to the height of the tree. In the worst-case scenario, such as a completely skewed tree, the height is equal to the number of nodes, n, resulting in a space complexity of O(n). In the best-case scenario, such as a balanced binary tree, the height is proportional to log n, leading to a space complexity of O log n. Additionally, the algorithm does not allocate extra memory for external data structures like arrays or hash maps. Instead, it relies solely on the recursion stack and a single variable to track the total moves. As a result, the space complexity is tightly correlated to the height of the tree, making it O(h). Let's break this down further with a best, average, and worst-case analysis. In the best case, the binary tree is perfectly balanced, meaning its height is log n. Here, the time complexity remains O(n), and the space complexity is O log n due to the recursion stack. In the worst case, the tree is completely skewed, resembling a linked list. This pushes the height of the tree to n, making both the time and space complexity O(n). For the average case, where the binary tree has a random structure, the height typically approximates log n. This gives us O(n) for time complexity and O log n for space complexity. These scenarios clearly demonstrate how the structure of the tree influences the space requirements, even though the time complexity consistently stays linear. Finally, let's compare this with potential brute force approaches to highlight the efficiency of the DFS-based solution. A naive approach might involve exploring all possible distributions of coins across the nodes. This would be an exponential time solution, as each configuration would have to be checked for validity, resulting in a time complexity of O(2 to the power of n, or worse. Additionally, these approaches do not effectively utilize the tree structure, leading to significant computational overhead. On the other hand, the optimized DFS-based solution leverages the hierarchical structure of the binary tree. By calculating excess coins in a post-order manner, the algorithm processes each node exactly once. This reduces the computational time to O(n), and minimizes memory usage to O(h), where h is the height of the tree. In summary, the DFS-based solution is exponentially more efficient than naive methods, offering linear time complexity and optimal space utilization, whether the tree is balanced or skewed. When tackling this problem, there are several common mistakes to watch out for. First, misunderstanding the problem requirements can lead to trouble. For example, failing to account for edge cases like a tree with only one node or a node already having the correct number of coins can cause your solution to fail during testing. It's critical to carefully read and understand the constraints and requirements before diving into the implementation. Another frequent issue is relying on inefficient approaches. Trying to simulate all possible distributions of coins might seem like an option, but this brute force method can quickly become computationally expensive, especially for larger trees, due to its exponential time complexity. Then, there's the risk of implementing depth-first search, or DFS, incorrectly. If you don't properly calculate and return the balance of coins, whether it's excess or deficit at each node, the algorithm may miscalculate the total number of moves, leading to incorrect results. Finally, some may overlook the properties of trees, such as their acyclic nature. Trees have a parent-child hierarchy, which simplifies the problem compared to cyclic graphs. Misunderstanding this structure could make your solution more complex than necessary. Another mistake to avoid is not accounting for negative balances. It's easy to assume that all nodes will maintain a non-negative coin balance during redistribution, but that's not true. For instance, a node may temporarily have a negative balance if it needs to transfer coins to its parent. This is an important detail to handle correctly. Now, in terms of solving the problem effectively, depth-first search, or DFS, is the key technique to use here. By leveraging post-order traversal, we can ensure that the surplus or deficit of coins at each node is calculated and passed up to its parent systematically. The main pattern to recognize is that the problem revolves around managing this flow of excess or deficit coins throughout the tree. Each node essentially acts as a checkpoint, contributing to the total moves required for balancing. A well-implemented DFS solution is optimal, with a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited exactly once. Be prepared to explain why simpler approaches, like brute force, are inefficient due to redundant calculations, and how DFS avoids these pitfalls. Additionally, keep edge cases in mind, such as trees with only one node, perfectly balanced trees, or scenarios where all the coins are concentrated at one leaf. These cases often come up in interviews, so it's essential to address them clearly. This problem also connects to several related problems that might help deepen your understanding. For example, LeetCode 124, which focuses on finding the maximum path sum in a binary tree, or LeetCode 337, the house robber 3 problem, both involve tree-based calculations. Similarly, LeetCode 543, which deals with finding the diameter of a binary tree, shares some conceptual overlap. Exploring these can provide additional insights into tree traversal techniques. Now, while recursive DFS is the most natural approach for this problem, you might also consider alternative methods. Iterative DFS or BFS can be used, especially since interviewers sometimes ask for iterative solutions to test your understanding of stack-based traversal. The trade-off here is that iterative approaches avoid the recursion limits of certain programming languages but require you to manage a manual stack, adding extra complexity. Another option is applying dynamic programming on trees. By memoizing intermediate results, you can potentially optimize certain calculations, but this approach is generally overkill for this specific problem. Finally, remember the core intuition: think of each node as a station where coins are exchanged with its parent. Clearly articulate how moves are calculated and emphasize the efficiency of your solution. This clarity will not only make your solution robust but also help you stand out in an interview setting. Great job making it to the end. We covered key aspects of the problem and discussed an efficient solution. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!